so the next time we can meet in person, either in India or Taiwan. Thank you all and enjoy the e-conference. Thank you.
Thank you, sir. Thank you, sir, for your encouraging speech for all of researchers. Now, I would like to invite our mentor, Professor D.G. Kuberkar, sir, to enlighten our research group in our area. Kuberkar, sir, please. जाने दो सर, नहीं होता तो
व्हाट्सएप नहीं चल रहा।
अच्छा जाने दो सर, छोड़ दो सर।
Dr. Hussaini.
जी सर।
I think Kuberkar sir must have got disconnected.
Yes.
Is he connected?
No, sir, he is not showing.
He's not there now. He must be having some network issue because today he is in hotel. He is in Ahmedabad for some reason, so he might be having some network issue there.
So may I request now our mentor, Professor M.D. Sidsat, sir, to enlighten all of us. Please, sir.
Okay, thank you very much. The president of this e-conference, Mrs. Khan Sabiya Begum, chairman of this particular function, principal of the Melia College, and one of my very good friend, Dr. Muhammad Ilyas, sir. Professor Mingling Sai from NTUST, he is my collaborator. Professor D.G. Kuberkar from Saurashtra University, he is also my collaborator. We have got very good, collaboration since last few years. Convener of this particular e-conference, Dr. Hussaini, and all dear participants. Good morning, everybody. At the outset, let me express my sincere gratitude to the organizers for giving me this opportunity to have interaction with all the participants across the country. As it is mentioned by Professor Sai, since last almost 2 years, we have been like all the academic activities have been locked. But in spite of that, in most of the Indian universities, we have been organizing a series of e-conferences, series of e-events, and all our teachers and students are actively involved in all those e-events. And somehow, although pandemic has restricted ourselves to meet through offline, events, but in spite of that, we have been meeting virtually through various events. And therefore, at this occasion, I would like to congratulate organizers, particularly principal of Melia College, my friend, Dr. Muhammad Ilyas ji, my PhD student, Dr. Hussaini. He has been very enthusiastic person. And I know like he has taken a lot of efforts to organize this event. And I would like to congratulate all the members of organizing committee as well, because you have provided wonderful platforms, e-platforms rather, for all the participants across this country. And I came to know that there are some participants from overseas as well. So this is going to be a wonderful opportunity for all the participants. And as it is mentioned by Dr. Hussaini, that most of the participants are young participants, like research scholars and master students. So this is going to be a wonderful opportunity for all the young researchers to learn something out of this event. And therefore, I'm not going to take much of time here because I will be speaking to you at length during my technical session. But I have one very, very humble suggestion to each one of you. I mean, those who are young participant of this particular event. Please don't miss this opportunity, because if you go through the technical program, you must have seen there is a wonderful combination of experienced professors and young professors as well. and they are going to share their exciting results with you. And this is going to be, as I mentioned, this is going to be wonderful opportunity for you to get yourself and reach. And therefore, try to be interactive with all invited speakers. I'm sure like every invited speaker is going to provide you enough opportunity to have interaction. So at the end of each invited session, I would request all the participants to have interaction with the resource person, to have interaction with invited speaker, because this is, as it is mentioned by Mingling Sai, Professor Mingling Sai and Dr. Husheni as well, that because of this pandemic, unfortunately, we are not going to meet, there would be a lot of restriction on us to meet physically. We are not going to meet very often. And hopefully this, whatever situation we have in India, hopefully we are going to have better tomorrow. And therefore, whatever opportunities we have today through this platform, please don't miss opportunity. Don't miss this opportunity. Have interaction with each and every resource person and get yourself and reach. With this, I wish you a wonderful time ahead, and I hope that you are going to enrich yourself through this technical interactive sessions. Thank you very much again, Dr. Hussaini, and thank you very much, Dr. Muhammad Eliadji. Thank you very much.
Thank you, sir. Sir Kuberkar sir is, I think he has joined.
Yeah. I am here. There is a network issue, but I am present. Yeah, I am.
Yeah. So, sir, I would like to invite Kuberkar sir to enlighten our researchers on this occasion of inaugural function.
Yeah. Thank you, Dr. Hussaini sir. So, my friend Professor Mahendra Sirsat from Aurangabad, Dr. Babasaheb Ambedkar Marathwada University, Professor Mingli Sen from the Taiwan, Professor Dr. Sheikh, and all the colleagues who are attending this conference, student friends. Actually, this is a very great opportunity, because when the request came from Professor Sirsat about this conference, I readily agreed, because you know that our friendship is not today's, but years before we started our friendship. And he came to my place, Rajkot, and I often go to his place, Aurangabad, which happens to be my native place. So this is a very good opportunity to online see each other and basically interact with each other, exchange our recent research and whatever the developments going on. And we are very fortunate to have an international speaker also, because we have Professor Mengli Si, he is from Taiwan, and I know Professor Sirsat has a very active collaboration in various Taiwan universities, because in one of my international conferences organized in 2016, he invited one of a professor from his collaborator from Taiwan, and we could interact with him also. So actually, this is the platform where we exchange our ideas, we exchange our thoughts, and the interaction which helps the student friends to build up their career, because basically research and development is a continuous process. Research and development is a continuous process, and this is a platform where they get the new ideas, new avenues, so that in future, when they want to apply for postdoc positions, research associate positions, faculty positions, they know what type of research is going on in India and outside India also. Because I know that the Taiwan universities supported by the National Academy of Taiwan, national institutes, they are doing excellent applied research, which is useful in the electronic industry and the sensor technology also, because they are in the forefront of the international applied research, like South Korea, Taiwan. These are the countries which have come out with a lot of devices. And I know that in the Aurangabad also, Professor Sirsat group, which is a very large group, which is in different colleges also in Marathwada, they are working, and they have very good sensor laboratory. They have very good laboratory in the nanomaterial synthesis also. So this opportunity every student should take and make use of this opportunity to build up their career and find out a good avenue, good way of doing high quality research, which is beneficial to our country and society at large. So with these few words, I will also share, after first talk, I will give my talk, which has been rescheduled by Professor Sirsat with my request, that I will also talk something about our recent results in the field of multiferrics, which is an area where I'm working from last 10 to 15 years. I used to work in high-TC superconductivity. So mostly my whole research career in the oxides only. So many people call me as an oxide man only. So because I did a lot of work in oxides since last 30 years, I have been working in the field of mixed oxides and the applied materials. So with these few words, I again congratulate the Jamia Millia College at Bid, which is at a very small town, but doing excellent work. This type of organizing such type of conferences with the guidance of Professor Sirsat, but the organizers, they always are doing a lot of groundwork for such type of organizing conference, and I congratulate them, principal of the college and the head of the departments and all the fellow faculties of the college, so for the organizing such a important conference. Thank you very much. Thank you.
Thank you, sir, for giving such a nice informative lecture for our researchers. Now I would like to invite the beloved principal of our college, who has cooperated and done a lot of for organization of this online event, Dr. Muhammad Ilyas Fazil sir, to give his inaugural speech. Sir, please.
Thank you, Shaukat Hussaini. First of all, Assalamu alaikum wa rahmatullahi wa barakatuh to all the participants, delegates, students, especially our Professor MD Sirsat sir, Dr. Kuber sir, Professor Mingli Sai, Anis and Ramesh Bise sir, and all students. I welcome you all for this online event and hope that you all are safe during this pandemic, and I pray to Almighty for safety of humanity. Dear friends, our institution are inspired with the goal to impart the education among minorities under the able chairmanship of late Mr. Ronak Ali and late Alhaj Ahmad bin Abood bin Mahfuz. The Anjuman Ishaq Talim was established in 1952, and then in 1991, the Anjuman established Millia Arts, Science and Management Science College. Right now, we run many educational institutes and units, and nearly 15,000 students are getting benefits at different level. All are ICT enabled. All our campuses are the ICT enabled. I feel proud to say that our college has very good contribution toward the research. 20 faculty members are recognized as a research guide and published more than 1,000 research papers at national and international levels. Friends, I would like to share with you that we have developed fully equipped research lab in zoology, physics, and electronics. Our faculty members have completed many research projects funded by national agencies like UGC, DST, and ISRO. Friends, to motivate the young researchers and faculties, our college has organized many national and international conferences. I hope this platform will fulfill the requirement of all researchers, academicians, and scientists. I am very much sure that this will open an opportunity to all you intellectuals for sharing their views, knowledge, and ideas. I hope the participants will make the best of this opportunity and will enjoy this online event well. I wish grand success of this event. Thank you. Thank you, sir. Thank you very much.
Thank you, sir, for giving such an inaugural function. Your speech will be really useful for us. So this is from the inaugural function. I would like to thank all the dignitaries who enlightened us for this inaugural function. I would like to thank the honorable principal for giving the inaugural speech and motivate all our colleagues in the college campus. Now, with this brief inaugural function, with the permission of the dignitaries, I would like to go for the technical session now. So may I start, sir, for the technical session? Sir?
Yes. Please go ahead.
Yeah, so for the first inaugural speech, for the first technical session, we are having with us, as I have told in the inaugural function, that Professor Mengling Sai, he is going to give his presentation. But before asking him to come and present his work, I would like to introduce him. He has a very big research CV, but I tried on my level best to minimize it in the period of time. That Professor Mingling Chisai is working as assistant professor in Department of Material Science and Engineering, National Taiwan University of Science and Technology, Taiwan. He is the senior engineer, LC Technology Department of AU Optronics Corporation. He is also the postdoctoral research fellow of the National Singh UI University on 1617. He was the visiting scholar, King Abdullah University of Science and Technology in 2016, of course, and he is also working as a research assistant at Academia Seneca in 2008. He has a foreign language qualification of TOEFL IBT score of 96. He is very expert in the different fields such as WR, RGB, gamma measurements. He is expert in physical vapor deposition PVD, chemical vapor deposition CVD, scanning electron microscopy, electron beam lithography, photolithography, finite difference time domain, and also very expert in the ultra high vacuum system. He has a very expert research fields of yummy way LCD color wash improvement. His field is also MVA LCD wash diffraction film design and simulation. Friends, he has large research fields, 2D material based optoelectronic devices, silicon organic hybrid solar cell fabrication and characterization, low light optoelectronic devices, water splitting devices, harsh electronics, nanotube fabrication for ion and electron microscopy. He has published many research papers at national and international journals of high repute. His CV is very long, sir, but his name is himself says that he is a great researcher. He is a great researcher in the region. People will ask him. So with this brief introduction, I would like to invite Professor Mengling Sai sir to present his work and enlighten our researchers in the region. Thank you, sir. Please.
Okay, thank you, Dr. Husani, for such a nice introduction. First of all, can I have the privilege to share my screen?
Yes.
Yes, sir.
Okay, let me try.
Yes, sir, you can share, sir.
Okay, thank you. I see. Okay, so can you see the slides now?
Yes, sir. Yes, sir.
Okay, thank you. The topic of my today's talk would be functional films for the next generation display technologies. Okay, I remember that actually 2 years ago, I was in at the almost the same time I was in India. I went to Aurangabad to visit Professor Shirsat, and then I went to the New Delhi to visit one of his friends in the, I think it's the International Accelerator Center. Okay, so it was a nice, very nice trip. It was also the first time I visit India. Okay, it was all very impressive, but it's not after that trip. I don't have any other opportunity to go to other countries. Okay, due to the outbreak of COVID-19. Okay, so after that we can only see each other online. Okay, hopefully next time we will have more opportunity to see each other offline. Okay, and as introduced by Dr. Husani, I'm currently working as an assistant professor in the Department of Material Science and Engineering at National Taiwan University of Science and Technology. Okay, and this is my email. Okay, so I will be very happy to receive or respond any questions that related to my topic. Okay, because this may not be very directly related to your research or your study. Okay, but if you have any question afterward, I will try to answer most of them. Okay, if I cannot answer right away, you can write to me and I will respond it as soon as possible. Okay, and this is actually the short version of the CV. Okay, before I joined NTUST, I was actually an engineer in the industry. Okay, so two of the most important industry in Taiwan. One of them, I think you may know, is about the semiconductor manufacturing. Okay, so up to now, from graduated from the college, most of the students graduated from the College of Engineering. Okay, will like over 50 or even over 70% will join the semiconductor manufacturing company. Okay, so this is the largest portion of students. Okay, but some of them, okay, if you want a better life quality, okay, you don't want to work in a very high pressure environment, okay, you will try to join the display industry. Okay, the second I think largest industry in Taiwan related to the electronic production. Okay, so that's what I selected. Okay, I joined the AU Optronics, is one of the famous display company in Taiwan. Okay, so the reason I want to tell you this is that one of my topics is actually more related to the display industry. Okay, and the reason I want to introduce this part is that actually there will be a difference when you are working in a company and you talk about the research, and when you are working in the university. Okay, the way of doing research may be different. Okay, in the company we need to evaluate the cost. Okay, the customers. Okay, we try to understand what our competitors like. Okay, but in university is more like a collaborating atmosphere. Okay, between the researchers. Okay, so the working environment is quite different. Okay, and the one other thing I would like to show you is that I visited the King Abdullah University of Science and Technology in Saudi Arabia, and it was a very special place, a very special university to visit. And since my thesis advisor, he moved there in around like 2014, I have the opportunity to visit there as a visiting scholar. Okay, so the experience is quite impressive. Okay, so if you are interested in visiting there, I can also share some of my my thoughts with you about this special university. And my research is basically focused on the development of optoelectronic devices. Okay, so in today's topic, I will mainly focus on the development of functional films. Okay, and synthesis of using the quantum dots to form the optoelectronic related films for optoelectronics applications. Okay, in the past, I also performed some work related to solar cells and photo detectors. Okay, but now since I am in the Department of Material Science, so I mainly focus on material synthesis and growth. Okay, and another topic of my research will be related to 2D electronics. Okay, and I mainly focused on the development, the growth of 2D materials. Okay, because especially the semiconducting materials. Okay, because this is more related to the semiconductor manufacturing industry. Okay, so if the student wants to go to the semiconductor manufacturing industry, I will encourage them to work on 2D semiconducting materials. But if the student wants to go to the display related industry, I will encourage them to perform the research related to the quantum dots or the functional films. Okay, so currently my research is more like industry oriented research directions. Okay, so before I go to the today's topic, I would like to list some of the works I have done during my PhD and postdoc career. Okay, so for example, in the past, I mainly focus on the device fabrication and measurement. Okay, so I work on using the silicon and organic hybrid solar cells to improve. For example, you can try to come up with some microstructures or nanostructures in order to improve the light harvesting behavior of your solar cell device. Okay, or you can try to come up with some silicon organic hybrid solar cells in order to improve the optical or electrical properties. Okay, maybe the conductivity can be enhanced, or maybe there will be some nanomaterials, for example, quantum dots, which can absorb light in the short wavelengths and then turn it into the emission light in the long wavelengths to improve the absorption of your solar cell. In addition, as mentioned by the Dr. Husani, so I also worked on the E-beam lithography technique. Okay, so if you have like any nanowire material or the 2D material and with small flakes, okay, smaller than like few micrometers, then I can actually try to come up with the nano devices using the E-beam lithography technique. Okay, and we also work on harsh electronics using materials such as silicon carbide or aluminum nitride. Okay, you know that since the development of like electric vehicles or the artificial intelligence, okay, the semiconductor with wide band gap becomes more important recently. Okay, so I also worked on some of those materials in the past. Okay, so the first part I would like to show you is one of the work I've done in the past with the AU Optronics, okay, with the local display industry. Okay, at that time, I mainly focused on designing the light diffusion films for improving the viewing angle performance. Okay, and the second topic I would like to show you is the work I am currently still working on, is using the perovskite quantum dot. We combine with some organic nanocrystals to come up with some films with improved stability. Okay, so I will start with the first section first. Okay, so first of all, let me compare some of the different properties of LCD, QLED, and micro LED. Okay, so the commercially available TFT LCD structure is shown in these figures. Okay, so first of all, you have a backlight unit. Okay, and there are two polarizers, one at the bottom of the liquid crystal solution, and at the top there's another polarizer. Okay, so the polarizers can convert your light emitting from the backlight unit to polarize the light. Okay, so when it goes through this liquid crystal layer, okay, the polarization of the light can be adjusted, can be changed by the liquid crystal orientation. And the orientation of the liquid crystal can be changed by applying different voltage difference between your top glass and the bottom glass. Okay, so the liquid crystal in the LCD is actually a switch, okay, to control how much light actually pass through this liquid crystal layer. Okay, so the control of the light passing through this layer can control the light coming out from your display, right? So based on the different brightness of red, green, and blue light, okay, you can actually decide, you can actually control the actual color displaying in your display. Okay, but for the OLED, it's something different. Okay, so for the backlight unit, for the TFT LCD, the backlight unit is always on. Okay, maybe for the high-end displays, they will prepare with some mini LED so that maybe at certain area of the display you want it to be black, they can turn it off to increase the contrast of your display, right? But for most commercial low-end or economical displays, the backlight unit is always turned on. But why you can see black image? Because you adjust the liquid crystal in a specific orientation so that the light would not pass through. Okay, the light would be black by the top polarizer. Okay, but for the OLED, okay, we come up with a device. Actually, this is a device with the top and bottom electrode, right? We have a hole transportation layer and electron transportation layers. Okay, so the electron and hole will recombine in the light emitting layer. Okay, so depending on the voltage you apply, you can control the brightness emitted from the light emitting layer. Okay, this is a more active device, okay, compared with the LCD. And recently people try to come up with this micro LED, okay, but there's still some challenge that you can imagine that in the past we have like only several less than 10 LED in the backlight unit, or like and with the light diffusers in the backlight unit. Okay, so we don't need to try to control the circuit or the voltage applied to the backlight unit. It was always turned on. We only control the liquid crystal part. Okay, but for LED, we need to think of it as each single device for each pixel, right? So it is still quite challenging to come up with like a 75-inch micro LED arrays and with almost no defect. Okay, so the price of the micro LED are still very high. Okay, maybe later on. And also the transfer technique of the LED is also it's also very difficult, okay, to achieve the almost 100% yield of such devices. Okay, so currently the mainstream are still LCD and OLED. Okay, so but for the LCD, there's some challenges, okay, some disadvantages compared with OLED. For example, okay, as I mentioned before in the last slide, okay, the brightness of the LCD is determined by the orientation of the liquid crystal, right? So the most challenging part for the VA display, for the liquid crystal display, is that when you look at different angles, you are actually looking at the different axes of the liquid crystal. Okay, and the different axes actually cause some light leakage problems. Okay, so if you there are actually different orientation for the liquid crystal. Okay, the one orientation is called a vertically aligned liquid crystal, VA LCD, and another type of the orientation is called the in-plane switching. Okay, so for the VA display, you can see initially you have a liquid crystal standing this way, and when you apply a voltage, you will turn to this direction. Okay, but for this direction, for initially at this direction, you can see that if you look at it in a large angle direction, okay, you are actually looking at the long axis of this liquid crystal. So there will be light leakage problem in the large angle, okay, light leakage problem. And this type of problem is actually solved in the IPS display, but IPS has its own problem, okay, because since it's always oriented in this direction, okay, for the liquid crystal display, it will have some light leakage problem in the normal direction, okay. So the contrast of the IPS liquid crystals display is actually restricted to like less than 1,000, okay. And as I talked about earlier, for the OLED, it's always active device, okay. So the contrast ratio of OLED can be very, very high, okay. So but for the OLED, there's other problems. For example, the stability problem, okay. So the light leakage, in order to solve the light leakage problem in the conventional LCD display, different strategy has been used, okay. But first of all, let me further explain the light leakage problem using this figure, okay. We always tune our transmittance versus the gray level this way by using a so-called gamma 2.2. It's actually an exponential of 2.2 curve shown in this figure, right? So when you actually tune your gamma in the normal direction to gamma 2.2 from 0 to 255 gray level, it will show in this black curve, right? But due to the light leakage problem, you will see that when we normalize the large angle direction transmittance, it will become this way. Okay, so you can see that at the mid level, there will be serious light leakage coming out from your display. Okay, so what really the effect you see on VA display, you can see that if you watch the TV in the normal direction, the performance is good. But if you watch the TV in a large angle direction, in the vertically aligned display, you will see some color washout problem, okay? This is mainly due to the light leakage coming out from the mid-gray level section. Okay, so what can be applied to solve this kind of problem? Okay, so previously many display companies try to come up with what we call the multiple domain solution. Okay, we can separate our single pixel into 4 domain or even 8 domain. Okay, you can see that for single domain, you will see that if you watch it in this direction, you will see black image. If you watch it in this direction, you will see white image. So there is a large color difference or the brightness difference. Okay, but if you design it to be multiple domain, you can see that from the normal direction, you see gray image. But from the large angle direction, you see half black and half white. Okay, but whenever you reduce this pixel to a higher resolution, okay, to a small area, okay, your eyes will actually average the black and white area. Okay, so you will see from your eyes, you will see something in between, similar to the gray from the normal direction. Okay, so this is one strategy widely used, adopted in the liquid crystal display. Okay, however, you can imagine that when you try to come up with this multiple domain design, additional circuit should be used, right? Which largely decrease the transmittance of your display, right? And the additional circuit will induce a reflection of your light coming out from the display. Okay, so the quality will also be decreased due to the additional circuit. Okay, and also the power that should be used must be increased, okay, to compensate the power loss due to the extra circuits. Okay, so people try to come up with new type of design. Okay, so this is what I was working on back in the industry. Okay, we try to come up with a polymer film on top of the display to solve this kind of problem. Okay, rather than design it into multiple domain, we try to come up with a more cost-effective way. Okay, we can simply attach some design, optical design on top of the display, so we don't need to change any circuit. Okay, but we can solve this type of problem. Okay, and the idea is basically by combining the structures with different refractive index. Okay, you can expect that from the physics that when you have whenever you have a periodic structure, okay, if the structure, the periodicity is close to the wavelengths of light, you can expect something will come up, which is called the diffraction. Okay, so this can actually be simulated using different type of software. For example, the RSoft or numerical FDTD. Okay, and if you make your periodic structure larger, okay, you need to consider the refraction. Okay, due to the refractive index difference, the light coming in will be refracted depending on the angle of incidence in the refractive index difference. Okay, and this can also be simulated. We just need to first measure the light coming out from our display, right? And we can actually simulate whenever it goes into a specific structure with a specific refractive index difference. Okay, what would be the outcome? Okay, that's what we want to solve. Okay, so this is just a scheme to show you that if you have different, you need to consider different color of light, right? For example, if you consider the diffraction phenomena, okay, you have a spacing of like 870 nanometer. Okay, with you have a periodicity of about a pitch of 870 nanometers. Okay, for different wavelengths of light, okay, it will be diffracted into different angle, right? You can see that the red light actually goes to the larger angle and the blue light goes to smaller angle. Okay, this can sometimes be observed by you emitting a light to your display. Okay, the pixel of the display can also cause the diffraction to happen. So you will see some light dispersion phenomena, okay, due to the periodicity of the pixel. Okay, and on the right you can see the refraction phenomena. Okay, due to the Snell's law. Okay, you can see that whenever you come up with a structure, okay, for example, we have a trapezoid structure here. Okay, at certain angle of incidence, okay, due to the different angle of this sidewall, okay, it will be refracted to another specific angle. Okay, depending on what? Depending on the refractive index difference of your medium. Okay, so you can see that for PET and PMMA, for different wavelengths of light, okay, the refractive index difference is shown here. Okay, and this actually causes a phenomenon which is different from the diffraction. Okay, as you can see, for the blue light, if we have a structure that looks like this, okay, the blue light will be refracted to about 40 degrees, and the red light will be refracted to about 35 degrees. Okay, so we need to consider both. Okay, if our pitch is smaller, okay, is related to the wavelengths of light. Okay, but for larger pitch, we only need to consider this one. Okay, so actually we performed some simulation. Okay, we performed some simulation, and we found out that there's one thing that would be quite important in our design is what we call the selective light diffusion behavior of the refraction structure. Okay, what is the selective light diffusion structure? We found out that if we have a light emitting in the large angle direction, okay, and the diffraction equation should be revised this way. Okay, so you will expect that for large angle instant light, okay, there will be some light diffracted back to the normal angle direction. Okay, however, for this type of design, okay, you can see that for large angle instant light, okay, it will be more portion of the light will be refracted to even larger angles. Only a small portion of light will be refracted back to the normal direction, okay, due to the total internal reflection at this interface, So this will cause a difference between the refraction structure and the diffraction structure in the contrast ratio of the display. Okay, so normally without any type of optical film, okay, we have a contrast ratio at 0 degree of about 3000, but for large angle direction, it drops to about 160. So what's the reason? The reason is what I mentioned before, is due to the light leakage problem. Okay, the large angle light leakage problem. Our goal is actually to increase the contrast ratio at large angle without sacrificing too much of the contrast ratio in the normal direction. Okay, but since we talked about in the last slide, for the diffraction, actually there's almost no selective light diffusion. Okay, so for large angle, for the light leakage in large angle direction, it will be diffracted back to the normal direction. Okay, this will induce a large drop in the contrast ratio in the normal direction. Okay, so you can see that for this type of design, there's not much improve in the contrast ratio in the large angle, but you actually sacrificing too much contrast ratio in the normal direction. Okay, so after this kind of simulation or evaluation, we decided to go for the refraction structure. Okay, for the refraction structure, okay, actually there's some other target we need to consider when we are developing this type of functional films on top of our display. Okay, we don't want to sacrifice too much transmittance, okay, because this will waste power, right? For the same brightness, we try to sacrifice for the same power, we try to sacrifice as small brightness as possible, right? And we don't want to reduce too much contrast ratio in the normal direction. Okay, so we can actually the transmittance drop can actually be determined by this angle here. Okay, we assume that we come up with a trapezoid angle. Okay, the trapezoid structure. Okay, the transmittance drop is actually determined by the angle and the height in the ratio of this part here. Okay, so actually we can do some simulation, okay, to control the transmittance drop. Okay, but later on we still need to compare what's the goal of the contrast ratio we want at the large angle and what's the goal of the contrast ratio for the normal direction. Okay, so we can come up with this kind of figures, okay, to evaluate. Before we adopt the optical film, Okay, the contrast ratio versus viewing angle is shown in the black curve. So you can see that in the normal direction, we have the highest contrast ratio. Okay, but it drops significantly in large angle. Okay, after modifying with the optical film, you can see that at large angle, the contrast ratio can be largely increased. Okay, and this one thing that I should mention is that for your eyes, actually, the increase of contrast ratio from like 100 to 500 is actually more sensitive than the contrast ratio between like 3000 or 2000. Okay, for 100 to 600, you will feel that the display is much improved. Okay, but for like 2800 and 3300, okay, actually for most of the people, you will feel similar. Okay, you don't feel much change between them. Okay, so based on this type of simulation, we can come up with different type, or we can try to design the improvement of our optical films in order to improve the viewing experience at the large angle. Okay, and actually you can come, remember we talked about this gamma curve here. Okay, in the normal direction, you can see this is an ideal gamma 2.2 is always tuned this way. In the normal direction, we fix it to like gamma 2.2. Okay, and you can see that this normal means without the optical film, you can see the light leakage coming out in the mid-gray level region, right? And by applying the design, you can see that this light leakage can be suppressed. Okay, so your curve will look more like this gamma 2.2 curve. Okay, so this actually shows that your large angle viewing performance is improved. Okay, and this is not the simulation result. Okay, this is actually the design we proposed, and we come up with a demo film. Okay, a small like A4 demo film. Okay, and we try to measure the contrast ratio. You can see that for a normal display, the contrast ratio at 60 degrees is like 100. Okay, and after we apply an optical film, okay, the contrast ratio at 60 degree can be improved by like 2 times. Okay, 2 to 2 times. Okay, and the transmittance loss is only like 3 to 5%, and this is acceptable. Okay, so the conclusion is that by proper design, we are able to achieve high transmittance diffusing films with excellent large angle picture quality. Okay, this is largely improved. However, okay, based on this type of design, there's still some side effect. For example, we found out that after the demo of this type of film, you can see that if we come up with a word like a U here, okay, you will see some blur of the edge. Okay, your edge become blurred. Okay, so this is quite annoying for us to know. Okay, but later on we found out that this image blur is actually due to the total internal reflection of the sidewall. Okay, of the sidewall. Okay, and also there's another side effect. Okay, what side effect? Remember we talked about the color dispersion problem. Okay, for a single angle trapezoid structure, okay, you can see that different color light tends to diffuse to different angle, right? So after you apply a film on your display, you can see that if we come up with a white screen, okay, at certain angle, you will see this rainbow color. Okay, this is due to the color dispersion problem. Okay, so later on, actually, I later on, actually, I left the company, right? But actually, my colleague, they continue to come up with new type of design. Okay, for example, how to solve this type of problem. Okay, multiple angle or a concave structure. What is a concave structure? Concave structure is a structure. I'm sorry, right now I don't have a structure illustration for the concave structure. A concave structure is like a rounded sidewall. Okay, a rounded sidewall, so that the image blur problem can be reduced. Okay, because your image blur is due to the sidewall, the internal total reflection of the sidewall, right? Okay, so you try to come up with rounded sidewall. Okay, and this image blur can be largely suppressed. And also the color dispersion problem is also because if you come up with a continuously rounded sidewall, okay, for different angle, there will be different dispersion. Okay, so you will come up with an average of a white screen. Okay, so your main rainbow, this is what we call the main rainbow Mura. Okay, this rainbow Mura phenomena can be largely suppressed. Okay. So this is about the first topic I would like to share with you related to the functional films for displays. Okay, and the second topic I would like to share with you is the one that I'm currently working on, still working on, which is the high performance perovskite quantum dot and the cellulose nanocrystal films with improved stability. Okay. So this is a simple introduction of the quantum dot. Okay, by reducing the dimension of the large crystal, we can induce the quantum confinement effect. Okay, so that for specific type of material, initially in bulk film, it does not emit any light. Okay, but by the quantum confinement effect, where some material, your energy level will become discrete, right? So your energy level become discrete. For certain material, the band gap will be in the visible light wavelength range, right? So for certain material, it will emit light, okay, when you excite it with a short wavelength light. Okay, you will make it to become like light emissive. Okay, so this is actually the background of the quantum confinement effect. So I think I will skip this one. Okay, but what I want to stress is what can it be useful in the display industry. Okay, for example, if we have a quantum dot, okay, the quantum dot actually the emission wavelengths can be controlled by the size of the quantum dot. Okay, so if you have a quantum dot solution with a high uniformity in your quantum dot size, okay, the emission width can be very narrow. Okay, the narrow emission width actually implies that when you look at this color gamut diagram, okay, at the edge of this color gamut diagram means single wavelength emission. Okay, single wavelength. So if your emission width is narrow, it will go to the edge. Okay, and we know that the display comes with three primary colors, right? Red, green, and blue, right? So if you have a high purity blue, green, and red light, your triangle here will be larger. What does the triangle means? The triangle means the color combination that your display can show. So the larger the triangle, you will get the better color performance from your display. Okay. And if we compare with OLED TV, okay, for OLED TV usually comes with white pixel, okay, to improve the brightness of the OLED. Okay, but for the white pixel, it's actually designed by using a blue OLED with a yellow phosphor. Okay, so there will be some additional emission around the yellow range. Okay, so actually your area will not be very large. Okay, but by using quantum dot, you can see 3 different narrow emission peaks coming out. Okay, so this can largely improve your color performance of the display. Okay, so and there's another problem for the OLED TV is that actually it's not stable, right? Because it's organic material. Okay, so your color actually changes with time. And for the QLED TV, the design is simply by applying a quantum dot film near the backlight unit, and you change the backlight from white light to blue light. Okay, so the quantum dot film acts as a color conversion layer to change the blue light to blue, green, and red light with narrow emission widths. Okay, so if we compare, this is the OLED TV and this is the QLED TV. You can see that under the same brightness, actually I really doubt it, okay, because I don't really think it's under the same brightness. You need to compare it in the same brightness. Okay, under the same brightness, you can see that the QLED TV shows better color performance. Okay, the image is more vivid than the OLED TV. Okay, so the quantum dot in display is actually shown here. Okay, this is the mass production of a quantum dot. Okay, and in this film, within this film, there's a red quantum dot and a green quantum dot. So if we change the backlight unit to blue LED, this layer will effectively convert the blue light to green light and red light. Okay, so you can see that this is the normal LCD, and this is a standard provided by the NTSC. Okay, so for the normal LCD is 72% area of the NTSC standard. Okay, and for OLED TV is 100. But for this type of a quantum dot enhanced display is almost 120%. And also this is a roadmap of the QD development in the display technology. Currently, we are still at the first stage. Okay, the first stage is using the quantum dot as the light conversion film only. Okay, but later, actually, people expect the development of the QD from the QD layer to like QD glass. Okay, and eventually, maybe we can come up with some QD pixels. Okay, currently the color filters are usually absorptions type of the color filters. Okay, so large of the energy is lost through the color filters. Okay, and if we change this color filter to conversion type color filter, okay, it will save the energy depending on your quantum yield. If you have a high quantum yield, your energy loss will be largely improved. Okay, and the final goal is actually come up with a QD-EL device. Okay, QD-LED. Okay, but this is very difficult because for this you not only need to consider the color performance, you also need to consider the electrical performance of your quantum dot and your related Hall transporting layer and electron transporting layer and the electrode. Okay, so this is the ultimate goal. Okay, and this also show you the roadmap, so I would think I will skip this one. And okay, so recently the commercially used quantum dot for display application is the indium phosphide. Okay, so it all started when 3M developed the first quantum dot display, actually the Amazon Kindle Fire ebook, okay, using this cadmium selenide quantum dot. Okay, you can see the quantum yield of this material is actually very high with very narrow emission width of 35 nanometer. Okay, but one thing that's not good for this material is that it's toxic with this cadmium element, right? So it will be restricted. Okay, it's already been restricted in the European Union. Okay, so now the mainstream is indium phosphide, and you can see the quantum yield is not as good, and the emission width is wider. Okay, but since it can pass the restriction, okay, so now it's still the mainstream. Okay, and recently people come up with new type of quantum dot called the Perovskite quantum dot. Okay, you can see the quantum yield is actually higher than the first two. Okay, and the emission width is very narrow. It's up to like down to like 20 nanometer. Okay, and even though it has the lead element, which is toxic, okay, but you can see the tolerance for lead is actually higher than for the cadmium. Okay, so it can pass, but the main problem for this type of material is that it's not stable. Okay, compared with the first two. Okay, because for these two, they are like we will design it into like core shell structures. Okay, but for this type of material, it's not stable. Okay, so I think due to the line limitation, okay, I will skip this part. Okay, and these are the two main synthesis process for this type of material, Perovskite quantum dot. And one is the ligand assisted reprecipitation. We first dissolve our precursors into a solvent, and we mix it. Okay, we mix it, and then we put them into another anti-solvent. Okay, so it will reciprocate inside this solution. Okay, another way it's used is called the high injection process. Okay, you come up with some precursors, and under high temperature, you inject it into a solvent. Okay, solvent. Okay, so you will under this temperature, the nanocrystals or the quantum dot will form in this solvent. Okay, and actually we can come up with a microfluidic reaction. Okay, people can come up with this microfluidic reaction to accurately precisely control the emission wavelengths of the Perovskite quantum dot. Okay, and other researchers try to come up with using a template, okay, as a synthesis medium. Okay, so you can see that the Perovskite quantum dot can form within this mesoporous materials. Okay, so you can use to achieve a uniform size of your Perovskite quantum dot. Okay, so these are the stability problems. Okay, the stability can come from the crystal structure. Okay, and the interfacial instability. Okay, usually for quantum dot we need a ligand at the edge of the quantum dot to encapsulate it, and it can use to prevent it from growing larger, right? But if your interaction between the ligand and the crystal is too large, then your material will dissolve. Okay, but if your interaction between the ligand and your crystal is too small, then it will not be able to protect it from like solvents or other from neighboring crystals, and it will be not effectively in prevent it from growing bigger. Okay, and also some environmental issues. For example, if you have oxygen, water, okay, you will react with this type of quantum dot. Okay, so different strategies have been applied. For example, we can use the compositional engineering to improve the structural instability. Okay, and we can use some surface engineering. We change the ligand, okay, to control the interaction between the crystal and the ligand, okay, to come up with a more stable nanocrystal. Okay, and we can use some encapsulation techniques to further prevent it from like oxygen or water. Okay, and this slide actually shows that the photo-induced aggregation process for the quantum dot. If we have like two neighboring quantum dot under light excitation, since the interaction between your ligand and the quantum dot is not very strong, okay? So under light excitation, sometimes your ligand will come off. And if you have two neighboring quantum dots, okay, you will grow bigger. Okay, this is called the QD aggregation. If it grows bigger, then the quantum confinement effect is lost. Okay, so your quantum yield will drop. Okay. Okay, so here is what actually we are studying in our group. Okay, we use the perovskite. We try to synthesize the chemical dispersed perovskite quantum dot in different solutions, and we try to evaluate the PL behavior of the quantum dot. Okay, and we actually characterize the size, and we try to come up with inkjet printable. Okay, this is very useful if you want to try to come up with a color filter type. Okay, you try to replace the traditional color filter with this conversion quantum dot color filters. Okay, and we try to come up with this QD parters. And recently we tried to combine it with cellulose crystals. Okay, this is actually derived from the biological plants, right? Okay, so we combine it. We try to use the functionalized cellulose crystals. Okay, and we expect that this functional group can have some interaction, okay, to stabilize the crystals. And of course, it can also act as an encapsulation polymer or like organic material for encapsulation to further protect the perovskite quantum dot from the various environments. Okay, and this is actually a schematic to show that it can be used to replace the missing halide to further stabilize the structure. Okay, and this is the preparation method. Okay, we first prepare a CNC cellulose nanocrystal dispersed solution and also the precursor solution, and we mixed it. We stirred at room temperature, and we use a vacuum filtration method. Okay, so that the perovskite quantum dot with cellulose nanocrystal film will form on the filter. Okay, we use a ceramic filter of like 20 nanometer size to successfully synthesis this hybrid film. Okay, and we evaluate the optical properties. Okay, we can see that for this bromide perovskite quantum dot, the emission wavelength is about 530, and we evaluate the absorbance, and we do the XRD to further confirm that the perovskite quantum dot form within the cellulose nanocrystals. Okay, and we also perform the TEM image, okay, to compare that the perovskite quantum dot within the cellulose nanocrystal. And this one is for pure perovskite quantum dot without using the cellulose nanocrystals. Okay, and by tuning the halide element, okay, we can actually control the emission wavelengths of our film, okay, from blue light to red light. Okay, and we can also combine the green and red films on top of a blue LED chip. And by placing different numbers of green film and the red film, we can actually control the color temperature of the white light. Okay, you see blue and red and green provides you the white light, right? But by controlling the numbers of films, okay, we can actually control the color temperature for the white light. Okay, and we also evaluate the stability. Okay, you can see that for this, we evaluate the stability of red film. Okay, because the red film is actually more unstable than the green film. Okay, so for the red film, in addition to the halide substitution, okay, we try to do some doping of zinc to further improve its stability. Okay, so you can see that under continuous UV, high temperature and ambient condition, this doped perovskite quantum dot with CNC all shows better stability under these three conditions than the hybrid films without doping and the colloidal quantum dot. Okay, so this tells us that the cellulose nanocrystal is very effective in stabilizing the perovskite quantum dot. Okay, so this is a short summary. Okay, so the functional, in the first section, I told I introduced the functional films with a refractive index difference that can be designed to improve the picture quality at the large view angles, especially for the LCD, right, liquid crystal display. It is important to prevent sacrificing too much viewing quality. Okay, you don't want to sacrifice too much in the normal viewing direction. Okay, you try to improve the large angle. Okay, so in the industry, when you're performing research, you need to know very specifically what your ultimate goal is. Okay, but for the if we doing research in the university, I think it will be more flexible. Okay, because you can have like different paths you can go, and there will be different outcome. Okay, but in the industry, there's always one goal that should be the priority. Okay, so you don't try to like go to another path and come up with another result. Okay, you need to focus because we need to compete with companies from the related industry. Okay, and so for the second topic, I talked about quantum dots that have been widely adopted in LCD panels to improve the color performance. Okay, and currently we are working on the full color hybrid films. Okay, so actually in addition to cellulose nanocrystal, we also try other organic materials, okay, that can be used to develop the films. Okay, but due to the line limitation, maybe next time I will share some other examples. Okay, so full color films have been synthesized with significantly improved stability, enabling the development for practical applications. Okay, and I expect that later on, we are working on trying to design some lead-free, okay, perovskite quantum dot. Okay, but up to now it's still quite challenging because the stability or the emission performance, okay, for example, the quantum yield is still low and the emission width is still too wide. Okay, it has to be narrow to improve the color performance. Okay, so I think this is if you need some hint on what we can do on related project, I think the lead-free perovskite will be a thing that we can think about or further discuss. Okay, I think that will be all of my presentation for today. And thank you very much. I'll be happy to take any questions. Okay, thank you.
Thank you, sir, for nice presentation. The participants are advised to ask or interact any question if they have. You can unmute yourself and ask the question to the resource person. If you are having any question, you may please interact with our able resource person, Professor Mingling Sai, sir, who has given the nice presentation.
Yeah, can I ask a question?
Yeah, please, sir.
Yeah, Professor Ming. Yeah.
Yes.
Yeah, this is Professor Kuberkar. Just I wanted to ask you, have you patented this some of the part for applied part?
You patent, right?
Yeah.
For this, I actually my company patent, and I was included with along with my colleague for the first part. And for the second part, actually, we recently submitted the patent application for the second part with using about the PQD and CNC part.
Okay.
Yeah, for this, but I'm not sure what the outcome is. Okay.
Gotcha.
So
yeah, one other thing, what about the stability issues? Have you faced any stability issues of these quantum dots?
Yes, of course.
Yeah.
Actually, what I didn't mention is that the stability. Okay, the stability as shown in these three figures, you see the stability is improved, but actually the quantum yield, the initial quantum yield is different.
Yeah.
Okay, for example, that for this hybrid film, the initial quantum yield is about like only 70 or 60%.
Okay. Yeah.
Okay, but for the colloidal ones, it can be like 80 to 90%.
Oh, that's good. Yeah.
Okay, so after it drops, it will be remaining will be like 50 to 40%, which I think should be further improved. And I think the drop in the quantum yield initially is due to that we use the vacuum filtration process. Okay, so upon the synthesis, there's some large crystals form on top of the film. Okay, so this will actually the quantum yield will be decreased due to the absorption of the large crystal, but it does not really emit the light we want.
Okay. Yeah.
Okay.
Thank you.
Okay. Thank you.
Anybody among participants, particularly students or research scholars, would like to ask any query to the honorable speaker of the session? Sumit sir, or any researcher, please. So thank you, sir.
Okay, thank you. Thank you.
Sir. I would like to thank the today's session resource person, Professor Mingling Sai sir, who has given the nice presentation. I think that his presentation will be nicely organized and it will be useful for all of us, and particularly the young researchers who are recently joined our research group or in the region. Now, thanks, sir, from my side. Lot of thanks. I hope that you will cooperate and we have such type of interaction with you in the future of our research career. Thank you, sir. Thank you.
Thank you.
So, dear participants, for the next session, we have with us Professor D.G. Kuberkar, sir, who is the professor in Department of Nanoscience and Advanced Material. He is going to deliver his talk on the multiferrics for new technology. But before inviting him for the talk, I would like to introduce, as in the morning session during the inaugural function, I have already told that he is our mentor. He has a nice or very big research experience behind him, but still I have tried to minimize his CV in a very short due to the constraint of time. So I would like to introduce him that Professor D.G. Kubarkar sir is working as a professor and head in the Department of Nanoscience and Advanced Materials, Saurashtra University, Rajkot, Gujarat. He has more than 30-year experience of teaching. He has completed 36 MSc projects so far. He has also 17 MPhil projects. Sir has having a research guide and PhD student doing under his research able guidance for 24. 23 have already completed their research under his able guidance. Sir has completed many research products of the total amount of 209 lakhs. He has completed 21 major research projects funded by the different funding agencies across the country. He has research collaboration with UGC, DAE, CSR Indore. He has the research collaboration with UGC, DAE, CSR Mumbai, FCIPT Gandhinagar, and ISSCR Bhopal, AUAC New Delhi, and Korea Institute of Science and Technology, Korea. His field of work is solid state physics and material science, superconductivity, multiferrics, magnetics, nanostructure, thin films, and devices. He has a foreign visit to France, the Republic, and Japan. He has 155 research papers in his reported journals, having a very handsome citations of 2 to 60 and H index of 29, while having H I-10 index at 70. He has the conference proceeding of 60 to his credit. He has many great achievements such as awards, 21 awards from the international and national agencies. He has published many books and he has a very great achievement. He has very great research experience. So with this brief introduction, I would like to invite Professor Dilip Kubarkar sir to present his work for our researcher. Thank you, sir.
Yeah. Thank you, Dr. Hussaini. Thank you very much for the introduction. And I thank the organizers of this conference. I thank my friend Professor Shirsat for giving me opportunity to share some of the results which have come out from my laboratory. And the main thing is that my students are involved very actively in the research. Since last 2-3 years, I have stopped taking the new researchers because now I'm on the verge of the superannuation. Next year, I will be superannuating at the age of 62. But since last 32 years in Rajkot, I could do some work which is useful to the society and basically the Saurashtra region of Gujarat. Because when you will now, I'll switch my presentation. I will share the present. 1 minute. I have to share the presentation. 1 minute. Share the screen. Yeah.
Yes, sir. You can share, sir.
Yeah. Is it visible now?
Yes, sir.
Okay. That's good. So I'll make it full screen. Okay. So because you can see here, I come from the Rajkot, which is a westernmost part of the India. That is very close to the Gir forest. For the international people, we are very close to the Asiatic lion sanctuary, which is the only one in the world where the lions are roaring throughout the year. And it's almost 100 kilometers, almost 50 miles from our place, 60 miles. So I come from the Saurashtra University, Rajkot, and the title of my talk is Multiferrics for the New Technologies. So this is basically in India. I come from this region of Gujarat. Gujarat is a state which is northern of Maharashtra, Mumbai, and this is a town in Gujarat, which is the 4th largest city. And our university is in around 350 acres of the land. And my department of nanoscience and advanced materials started in 2015-16. And this university is one of the largest universities in the Gujarat state. Okay. So now this is my department in the stopgap arrangement. This is from last 5 years we are housed here, but we will be going to our new department building very soon now. Plan of my presentation is that I will be talking about the multiferrics because I understand in the inaugural session, the organizers told that there are a number of master's students because your college is also running the master's program. And there is a very interesting class of the students, which I always focus rather than a master's students. I'm very much happy to give the understanding of the subject to the the graduate students who are doing the last year of their graduation, that is the BSc third year students, because who have taken up the physics as a major subject, that is honors or major subject, and they are feeling that they should go for the masters in physics. So these are the students. I always feel that we should encourage them. We should give them more knowledge about what is in the physics or the new materials, so that when they select the masters, their mindset is already decided that they will be doing very good quality masters and pursue the research and development in this field. So with that in mind, I have introduction slides for the multiferrics. These are very interesting because since last 5 years, I started the MSc Applied Physics program integrated. This is after 12th science, A or B group. The student can come here in my department and they can do the 5 years course. First 3 years is BSc Applied Physics and 2 years is a master's. This is on the same line of the ICER program, because ICER pattern is very successful in India. So I also started, this is the first program in Gujarat state, 5 years integrated. So that we can have some good students for the 5 years. So this multiferrics is one of the topics at the master's level now, because the functional materials paper is there for the master's, that is semester 3 and 4. We have got advanced materials and functional materials. So I'll tell about the multiferrics, and then I will be just discussing about the results of the calcium doped BiFeO3. BiFeO3 is a very interesting multiferric material, which is a ferrite. And then I will talk about the calcium doped multiferric materials. So these are my collaborators. I should thank all the collaborators from the RRCAT. That is, I am using the Indus 2 and Indus 1 facilities, which are national facilities for all the users. I am associated with UGC DA CSR from last 28 years. This is TIFR, where TIFR is a Tata Institute of Fundamental Research. There also I did my PhD work. I was registered in Aurangabad, but I did a lot of work in the field of high tissue superconductivity in 87, 88 up to 90. And this is FCIPT Gandhinagar. This is for the plasma technologies. Then this is an institute which is called as Inter-University Accelerator Center, where Professor Sisat is also very active in this. And I am associated this institute, which is a UGC body, which is Autonomous Institute of University Grants Commission. This is accelerator. This is one of the largest accelerator in India. This accelerator can go up to 400 MeV, 500 MeV machine. And here I am associated, and I was a chairman of the accelerator user committee for the 3 years. So these are the collaborators with whom I collaborate and use the facilities, and I could do some good quality work useful for the society. So these are the Indus accelerators, because I think in your master's classes, your teachers will be teaching you about the Indus. But it is a very good time whenever the pandemic situation is over and the permission is given, everybody should visit one of the great facilities, Indus 1, which started long back, and Indus 2 has started almost 15, 18 years before. So this is a very good facility, Indus 1 and Indus 2. These are the two major facilities which are used for this, and these are lot of this thing. And in Taiwan, there are large number of synchrotron facilities. Like we have only one in India, but Taiwan maybe every 100 kilometers, 200 kilometers, there is a synchrotron facility. So therefore, India should think very seriously to have good quality research with the help of synchrotron facilities. So these are the Indus 2 facilities, and large number of beam lines are available. I am using this BL1 facility, small lumbar X-ray scattering facility, and this BL1 beam line I am using in the Indus 2. So coming to the multiferrics now. If I'm going fast, you can just send me a message also, that be slow, because I have to cover so many things. So I'll be a little faster initially. So these are the multiferrics. Multiferrics are a very interesting class of the materials, because they possess 2 or more than 2 ferric orders. They possess 2 or more than 2 ferric orders, basically. You can see, you can have either ferromagnetism and ferroelectricity in one compound, which is very, very rare type of materials, or you may have ferroelectric and ferroelasticity in the same compound. So 2 or more than 2 type of the orders can be present, and this is an interesting one. So therefore, you know, if you happen to see the Maxwell's equation, one of the Maxwell's equation has got the magnetic and electric fields both combined together. So this is the one, a material where the electric and magnetic effects, both the effects are present in the same material. Therefore, multiferrics are attracted a lot of attraction in the last 1.5 decade. That large number of publications and devices are coming, which are replacing the conventional devices. So what are multiferrics? For the students, these are not for the expert people who are sitting in the audience. Suppose you apply the electrical field. Suppose you apply the electrical field, you get magnetization in the material. Material exhibits magnetic behavior. And if you apply the magnetic field to the material, you get the electrical polarization in the material. So this is called as a magneto-electric effect. Very interesting effect, that crisscross electrical field application gives magnetization, magnetic field application gives polarization in the material. Is it not a very interesting material? Then there are other materials you must have studied, piezoelectric materials. These are anyway, you know what are piezoelectric materials, application of electrical field, how you get the change, and if you apply the stress, how you get the electrical field. That is reverse piezo and piezo. Then there are different type of other materials which are called as magnetic shape memory alloys. So here you can apply magnetic field, you can get some physical variation. If you apply some stress, you get magnetism. These are the shape memory alloys. So many people are working on the shape memory alloys. So therefore, magnetoelectric effect is introduction of polarization by application of magnetic field, introduction of magnetization by application of electrical field. So therefore, these materials are very unique materials, and very few of the compounds exhibit multiferric effect and magnetoelectric effect of the first and second order. Now, these multiferrics are classified into two types. This is for the students, basically, I'm telling, because type 1 multiferrics, these are the two types of type 1 multiferrics. Here, the magnetic origin and the polarization, origin of polarization and origin of magnetization, they are independent of each other. Okay. So independent, that magnetization in the material and polarization, their origin is totally independent. But type 2 multiferrics are more interesting, because here the origin, magnetism drives the polarization and electrical field drives the magnetization. Very interestingly, both have got a very interesting mechanism. So application point of view, these materials are very interesting, and these are different classes of the type 1 and type 2 multiferrics basically. And we are working in the lone pair multiferrics that you can see here: BiFeO3, bismuth ferrite, bismuth manganite, BiMnO3, then lead FeO3, lead manganite, lead cobaltite, and so on. So these are bismuth and lead based oxides basically. Mostly lead is avoided by many of the applications because these are toxic in material, but basically mostly bismuth based materials are used for applications because of their interesting behavior. Then there are some geometric multiferrics also. These are hexagonal RMnO3 type of compounds, where recently we have done some interesting work on the magnetism of these materials. Very interesting magnetism has come out in these materials. And then exchange structure multiferrics, this is RMN204. These are called as polinear spin orders. These are spin chain compounds. So here also a lot of work, but these are very difficult to synthesize. Also, BiFeO3 is not so easy to synthesize in a single phase, but we have to master the synthesis technique. A student has to learn minimum 6 months. Minimum 6 months he has to spend time in the laboratory and try to get a very good very good quality single phase sample, because it is always said, my mentor who was in TIFR used to say me, Kuberkar, look, making a very good quality sample, single phase, very good quality sample is half the battle won. 50% of battle is won in the research if you can make or you can synthesize a high quality sample. That means it is going to give you the desired properties if the quality of the sample, phase of the sample is very pure phase and single phase. So with this, we tried a lot, and I'm talking about almost 10 years before. Now it is highly stabilized now. Everything is very clear, but we tried 10 to 12 years before, and we could successfully synthesize very good quality BiFeO3. So BiFeO3 is it has got a ferroelectric transition temperature of 1143 Kelvin and antiferromagnetic transition temperature of 643 Kelvin, which is quite high as compared to the room temperature, and therefore its applicability is quite interesting, because any device which you make, just now we saw the very interesting part by the earlier professor told that nowadays everything has to be, the ambient temperature should be as to room temperature, because any device which works at very low temperature, its properties, it is not very applicable for the day-to-day life. So therefore these materials have got transition temperatures very high, and it has got a G-type antiferromagnetism. I will not go into details about what is A-type and what is all these different types of antiferromagnetism depending upon the ordering of the in-plane and intra-plane ordering. And it has got a modified cycloidal spiral of the wavelength of 620 angstrom, and the propagation direction is 110. So this is an interesting compound, BiFeO3. But when you want to use it for some application in a device also, there are difficulties. Difficulties actually come across when you use these for the practical applications, because these BiFeO3 materials, they have got a very high leakage currents. Leakage currents are very high. They have got small remnant polarization, which is not a very good for the application basically. And then lastly, remnant polarization means when you switch off the electrical field, whatever the polarization remains in the material. And then they have got an inhomogeneous spin structure. So this restricts their application or applicability of this BiFeO3 and its derivatives or the substituted BiFeO3. So what happens now, these leakage currents, this is because of the deviation from the oxygen stoichiometry that leads to the origin of the leakage currents, basically, because there is a change in the oxygen state of Fe ions, Fe3 plus to Fe2 plus and so on. And because of that, this takes place via the oxygen. You can see that indirect type of hopping is there, Fe3 plus getting converted and Fe into Fe2 plus by oxygen. Then, but there are different approaches. Because I always say to the students, there are difficulties. Research is full of difficulties. Research is full of challenges. But a true researcher should never give up, because you are doing expert research. I think most of the people who are listening or attending this e-conference, they are expert researchers. I don't say that theoretical research is not challenging. It is also challenging, but expert research has lot of things which are always to be looked at. Actually, it is right from the quality of the powder which you are taking or the quality of the chemical which you are selecting up to the applicability of the device. So therefore, there are approaches. There are different approaches to overcome the difficulties which are faced in the BiFeO3. The first approach, which is very popular, and we are material scientists. So basically, I always say that we are basically solid state chemists. Actually, we have to become solid state chemists, because we never thought about chemistry as important. Now we feel when we do work in the mixed oxides and we work in the new material developments, chemistry plays a very important role. So therefore, the first approach is that doping and formation of BiFe3 based solid solutions. So therefore, you substitute either rare earth in the bismuth side, you substitute some alkaline earths, strontium, lead, barium, calcium in the bismuth side, or directly at the Fe side, you substitute with some transition metal, 3D elements, MnCO, chromium, titanium, nickel. So if you do this is called as chemical doping. This also helps in overcoming some of the difficulties which are faced in the use of BiFeO3. Then, application of high magnetic field. Application of high magnetic field also takes care of the inhomogeneous spin structure, and therefore we can make this material for the applied purpose. And lastly, but not the least part, that is the development of the strain or modification in the strain and the material. And this strain can be modified only and only if you can grow this material in the form of thin films, that is two-dimensional materials. Because just now we saw a lot of interesting results on the films actually. So therefore, films are very important for the device, for any type of applications. Your normal powder material is of no use or bulk materials are no use. So we have to make very high quality films. And then if you can modify the strain in the material, then you can take care, you can have the overcome some of the difficulties of using the BiFeO3, that is making of the very high quality films. So therefore, these, as you know, that different types of memories are there. So for those who are sitting with the undergraduate people and postgraduate starting the people, you know that memories are very important for any applications now, volatile and non-volatile memories. And mostly we are talking about non-volatile memories in applications, that is ROM memories and RAM memories. So in the RAM memories, you can see here, these are interesting memories: magnetoresistive RAMs, phase change RAMs, ferroelectric RAMs. So therefore now people are, as I told you, Taiwan, Korea, Japan, these are the people who are at the very forefront of the development of these memory devices and the new advanced spintronic devices. So therefore, you can see here in development, people are working about conductive bridging RAMs, then CB RAMs, resistive RAMs, racetrack memories, nano RAMs, millipede RAMs. These are some of the new memories which are coming, and they are actually changing the complete scenario of these new type of electronic devices and new type of the what you call as the laptops and your computers and all these devices. So therefore, these are some of the memories. Now, because you know that resistive random access memory, you can do two types of switching. One is a unipolar switching, another is a bipolar switching. This is a bipolar switching basically here. So therefore, you can switch off the applied voltage. You can switch on the bias voltages in both the way, plus and minus, and you can do the bipolar switching actually. In unipolar switching, resistive switching, it is but the same polarity, voltage of the same polarity, but in different magnitude. But in bipolar switching, one polarity is used to switch the HRS, means high resistance state, to low resistance state, and the opposite polarity of the your bias voltage is used to switch back to the HRS stage, from HRS to LRS, and from LRS to HRS you have to switch the applied voltage polarity. So therefore, bipolar switching is mostly used in the applications of the device. Now, magnetoresistive random access memories. Here you can see here, these are non-volatile computer memories. Electricity is only supplied for data rating, but not for the data storage. Therefore, the data stored in the MRAM is a permanent data basically. So these MRAMs does not lose its memory when there is no power. So these are very interesting MRAMs basically. We are always using these MRAMs in our day-to-day applications basically. And these density of the DRAMs now. So these type of the new RAMs, these are non-volatile flash memories. So you can see here, I have compared here different types of the memories, MRAMs, then speed torque MRAMs, then flash RAM, DRAMs and SRAMs. And these are their thicknesses of the films. And you can see here the read time 10 nanoseconds. And now lastly in the SRAMs now, you can see that it becomes one nanoseconds now. So therefore, very fast switching RAMs are being developed nowadays. And at the base of all these developments of devices is the new materials. Therefore, I always say that this 21st century will be always about the new materials, development of new materials and their applicability for the betterment of the society. That is what now we are thinking. Just now we saw a lot of interesting thing about the display devices now. Very soon now, latest new type of display devices are coming now. So therefore, these memory devices also, new type of materials are involved in the development of these. So I will not go into the details of these different MRAMs, how MRAM works, then ferroelectric RAMs, how FE-RAM. This is a part of the syllabus now. Mostly we teach to the students about these applied. These are applied materials technologies basically. FE-RAMs, MRAMs, resistive RAMs, millipede RAMs, and so on. Actually, these are phase transition memory. These are phase change memories, PCMs now. Nanotube RAMs are there. Then flash RAMs. That is what now you can see here. This is very familiar picture with all of our listeners now. These are our flash. These are flash RAMs actually. These are electronic non-volatile computer storage medium that can be electrically erased and reprogrammed. That is what we are using in the day-to-day life now. Okay. Now, here, when you're talking about different types of the advantages and disadvantages, you can see here. Okay, you can see here that data is stored by the magnetic storage elements. Elements are formed from two ferromagnetic plates, each of which is held in a magnetic field separated by a thin insulator layer. So therefore, you are to make a multi-layers. All these memories are in the form of the multi-layers now. These are the advantages of the MRAMs now. These are some of the disadvantages also, because you know that the power requirement of the MRAMs now, these magnetic random access memories, power requirement is very high as compared to the reading and the writing data, because 3 to 8 times higher than power required for the reading data. So writing is a little bit costly in terms of the power requirement as compared to reading the data. Mostly we have to write the data also in the memory before you read it. So therefore it is little bit a costly affair, because it takes a lot of power requirements are more. These are the advantages of these disadvantages. So then speed of the current MRAMs now. The current speed of MRAM is 57 megabytes per second. This is a quite good speed which is used. This is fully random access mode and therefore has no latency. So latency effects, that is delay effect. Delay effects are avoided in this type of the MRAMs now. These are some of the advantages which we have to always think now. So now what are the different types of FE-RAMs now, ferroelectric RAMs? It has got two types of configuration. That is one transistor, one capacitor configuration. Another is simple one transistor capacitor actually, one transistor configuration. And therefore we have got a destructive readite. Here it has a non-destructive readite. It has got a MIM structure, metal, insulator, metal. It has got a metal ferromagnetic insulator, then semiconductor substrate. So these are MFI structure. These are metal ferroelectric insulator semiconductors. You can see how these are there. Metal ferroelectric metal. These are a simple structure. It has got a 1T, 1C. One transistor, one capacitor configurations are there in these FE-RAMs now. So now I'll not go into more details because half of the work basically I have done for the initial things only. These are hyper advanced level of integration to upload gigabyte non, because now the time has come that we are not talking about megabyte non-volatile RAMs now. Megabyte has gone now. Now because the advancement in this research in these RAMs, the memory devices, that is so fast that people are talking about gigabyte now, G-byte non-volatile RAMs, and these are replacing the conventional megabyte RAMs now. So here the different types of 1T, 1C FE RAMs are being used for the gigabyte applications, non-volatile applications. And these are the resistive random access memory. After FE RAMs now, these are RRAM, that is resistive random access memory. You can go from the HRS to LRS state in a by switching the polarity of the these are basically made up of the CMOS structures, complementary metal oxide semiconductor processes now. Okay, so these are racetrack memories. I'll not go into details about the racetrack memories. These are domain wall memories basically. Now this is how the memory reading and writing takes place. Actually, this is a schematic that how the reading and writing takes place in these type of memories now. Okay, so challenges are there. So basically there are challenges in the development of the memories and the memory technology, because here two things we have to always optimize. One is applied magnetic field and the electrical field which are created, or applied electrical field and magnetic effects. So these are the two very, very important things. Then light irradiation levels, pressure and temperature. These are the two to three things which always have to be taken care very seriously when you are optimizing the use of these memory elements or memory devices. So these are the some of the manufacturers of the random access, the resistive RAMs now, random access memories. You can see Hitachi, Intel, Samsung, Seagate. These are the leaders in the manufacturers of the memories. So these are the comparisons. I will not go into the details. This is for the technical engineering side, because it is always said that a material scientist makes good quality material. He makes a device, and engineers will make that device into a reality and make them, they will put them in the factory or whatever the industry, and it will be marketed. Marketing people or the management people will market it now. So but basically the main work is by the material scientists like you and me, that we have to think about new materials which are useful for the new and new technologies. So therefore this is a comparison of different types of the memories now, and you can see the speed of the MRAMs, and this is around 10 nanoseconds which is there. Okay. Now, that you can see for the layman now, very easily we can explain that these memories are used everywhere. You can see industry and transportation, then cache memories for them. These are the cache memories now. Mobile phones, everything we are talking about. Whenever you select a mobile phone in the market, you always go for the memory. You go for the display, how much megapixels and all this display. Just now we'll learn about the display technologies, what lot of new developments. Then you talk about the memories. So these are the two things we always go for the mobile. We never worry about weight and everything. We always worry about what is the speed, what is the memory, what is the display, what is the megapixels, how much is the camera, and everything. That is all. Then mass storage memory. These are also hard disks now. And as you know, maybe in Taiwan it must have come. Now we are talking about the hard disks now with these nanomaterials in that. You can have up to a size of your thumbnail now. A thumbnail with a capacity of around 10 terabytes. 5 to 10 terabytes is very, very common hard disk capacity. Now in India, we have got 1 terabyte now. 1 or 2 terabyte hard disks are available in around, I think 30 pound or 40 pound, mostly 30 or 35 pound. We get around 1 terabyte or 2 terabyte hard disk, but they are quite large in size. But if you go in the advanced countries now, which are developing all these things now, the hard disk of the maximum size of 1 square inch now, 1 square inch and a capacity of 10 terabytes. You can think about the memory. All your whole life's work can be stored in that hard disk, and you can put that hard disk in the tip of your pen as a pen holder, and everything you can just switch in and you can just do whatever you want to do. Then you are talking about embedded MCUs, smart cards everywhere. These SIM cards also, these are again non-volatile memories, ID cards and everything, smart meters. So you can see that these are very interesting part of the applications. Now, after completing this, now I will just talk about some of the results. This is for the people who are already doing the research or who wants to take up the research, that how can we proceed the material synthesis, and then how one can go for the characterization. Because I told synthesis of the films, very high quality films. If you are talking about the device, then you have to talk about the epitaxial films, single crystalline epitaxial films. We have to grow in a very good quality ambient atmospheres, and then you talk about the how to characterize the film and then use it for the device applications. So thickness dependent studies on the calcium doped BiFeO3. So I have selected 3 thicknesses, 23 nanometers, 43 and 63, and these thicknesses were tried 2 or 3 times they were confirmed by different characterization techniques now. So why the motivation for undertaking this work? I wanted to see the effect of film thickness on the modifications in the electronic structure using X-ray absorption spectroscopy measurements. How the electronic structure gets modified as a function of the film thickness. And then, as I told you, one of the technique to take care of the restrictions of their use of these materials, they strain. So strain-induced modification, they're rectifying IV characters. These materials, they have got a rectifying IV behavior, and the effect of film thickness on the resistive switching behavior. These were 2 modifications basically. These are the calcium doping between 10 to 15%. This was our study, and earlier some reports were there that 10 to 15% of calcium you get the pseudo tetragonal phase that has a considerably smaller C-axis lattice parameters. So we do some literature survey, which is always there. At least 3 to 4 months, a student has to put his head into the literature survey and get the overall idea what has been done through some review article. Instead of individual article, you can go to a very exhaustive review. Every year, once or twice, review articles comes in your area of your interest. So read the review. Review will have hundreds of the references will be there in the review articles. So you can find out which is the best material, which composition is best suited for your research, and you can synthesize those materials. So therefore, I synthesize these films, BCFO films, these are calcium doped BiFO3 films, using a PLD facility. Now in my department, I have established in last 3 years, I have got a pulse laser deposition facility, which is used and regularly used. But earlier I used to use the facility of UGC DA CSR. These are the KRF, this is krypton floating excimer laser, and these are the laser parameters. And this is the substrate. This is the niobium dope STO. This is N-type substrate, because my material is a P-type material. So basically we are growing a PN type of NP type of diode or PN junction diode in the form of thin films, that is P-type materials, which is deposited on the N-type substrate, which is oriented substrate 100 single-side polished substrates. So therefore, these are the powder diffraction peaks actually, and I have developed the physics department when I left in 2015. I have developed full-fledged facilities of XRD and everything. All facilities under the roof are there in the physics department now. So this I developed when I was there for last 25 years. So here these are the XRD X-ray diffraction pattern, and here you can see that you can find out the strain using the formula, which is very popular formula for doing the strain, whether it's a compressive, whether it is a tensile strain or a compressive strain. So I saw that the strain varies from -3.36 to -3.34 with increase in the film thickness. So film thickness increases, the strain value that always changes. So you can see here the strain is dependent on the film thickness, which is a very popular or the well studied. So in order to know the epitaxy of the films, one has to perform the phi scan studies for the student who start their career. Just simple XRD doesn't work for the films. You have to do the phi scan measurements. If you want growing the single crystalline epitaxial films, you should know the orientation of the films. And once you know this, then you can do phi scan measurements, and then you can find out you can do the X-ray reflectivity measurements also. These are X-ray reflectivity XRR reasons. You can set up your setup for the X-ray reflectivity, and from the fringes and from the calculations, then you can find out the thickness of the films also. The thickness of the films were found out from the X-ray reflectivity measurements. And the next, after doing the structural understanding about the films, if one goes for the what type of the grain morphology is there as a function of the film thickness, what changes in the grain morphology takes place. So therefore, with increase in the film thickness, the grain morphology becomes more and more uniform. And this was done using the atomic force AFM facility, which is available in the IUSC New Delhi. In my department now, the money is lying. I have got around 3 or 4 crores rupees with me. So maybe very soon now, when we go to the new building, I will be having a full-fledged AFM with the piezo arrangement, with the PFM arrangement with him, piezo force microscope with it. So this is AFM of the film. So with the film thickness, the grain morphology becomes more and more uniform now. And then you can do the Laplace transfers. You can find out the film thickness as a 23 nanometers. And then if you have a higher thickness film, the well-developed uniform grain structure takes place. As the thickness increases, the grain structure becomes more uniform and uniform. Okay, then these are the SEM. This is grain morphology studied using the SEM, and these SEM studies, they validates the XRD results and the FM results. And the 23 nanometer films, we have got some whites are observed, but whereas 43 and 63 nanometer films, we have got a uniform structure as compared to the lower thickness films now. Okay. Now, this is RBS facility. This is only available in IUS in New Delhi, which is gifted by the Maryland University. And last 15 years, this facility is available. Rutherford backscattering RBS, and from the using the RUMP simulation software, you can simulate the you can simulate the number of counts versus the channel numbers. You can simulate the data, and then you can experimentally verify also. And the composition, average composition of our film, which was bismuth 0.9, calcium 0.1, Fe 0.95, calcium 2. You can find out all this composition by analyzing the data also, and the thickness was again confirmed. The thickness which you confirm, you studied, measured using the XRD, using XRR, it was confirmed that it is 24 nanometers, 45 and 62.9. Instead of 63, we got 62.9. So almost whatever the X-ray XRR measurements, we were confirmed using the Rutherford backscattering. This is the second confirmation of our thickness of the films now. And then we do the ellipsometry studies using the FCIPT facilities. Again, two aims. One is to fit the thickness, one has to know the thickness confirmation using the Cauchy model we used, and then we use the ellipsometry studies here. Okay, and then we found out the sub-band gap features. We have got the absorption sub-band gap features at 2.47 electron volts due to the collective excitations of band gap, and then these are arising from the defect states in the material. So this has been already published 2 years before. Then these are the photon energy versus the alpha E square. So these plots also, this also confirms that the broad asymmetric peak comes at 2.47 nanometers, 2.47 electron volt in 23 nanometer films is a sign of presence of defect states. So there are defect states which are available or which are present in the lower thickness films basically. So this is the, after doing the these measurements, then we move on to the X-ray absorption spectroscopy to study the electronic structure modification. What happens to the electronic structure as a function of the film thickness now? These measurements were taken using the facility of the Indus 2 facility, that is RRCAD. So we did the that is oxygen cage X-ray absorption spectra, and here we studied, we completely fitted this complete data, and after fitting the data, we saw that A1 and A2 features, because these A1 and A2 features are assigned to the hybridized Fe3D and oxygen 2p orbitals in the octahedral crystal field symmetry, and the feature B has a distinct nature in as compared to 23 nanometer film, which is a blue film, as 23 nanometer film. The 43 and 63 nanometer films, in the 43 and 60, that is red one, and this almost green or dark blue, you can see that feature B is totally different. So therefore, this observed dip and the separation between A2 and B, this separation, A2 and B separation, this increases with increase in the film thickness. As we increase the film thickness, you can see the separation increases. The separation is not clearly observed in the case of 23 nanometer film, suggesting that the electronic state related to Fe3D EG orbitals, oxygen 2p and bismuth 6x oxygen 2p are overlapping with each other. So therefore, these are our some of the observations after fitting the oxygen cage X-ray absorption spectra. Then we deconvoluted the oxygen cage absorption spectra, and then we studied that the peak intensity ratio between EG and ET2G, these are the two different types of the energies, ET and T2G, that decreases from 7.42 to 2.32 from 23 to 63, highest thickness film, with the increase in the film thickness. What this suggests? It suggests hybridization between oxygen 2p and Fe3D orbitals. It increases, which increase in the film thickness, and this also there is a decrease with the increased film thickness. So therefore, we normalize the FeL32 as X-ray absorption spectra, and we again the same facility being Indus 2. So here, interestingly, we observe the crystal field splitting. So the value of the 10 DQ crystal field splitting value varies between 1.49 to 1.44. Theoretically and experimental values, they match with each other, crystal field splitting value, which can be understood after normalizing and analyzing this data. And then coming for the application side, after doing the modifications in the electronic structure as a function of thickness, we study the IV characteristics. This is our normal setup. which is facility. I made a simple arrangement in IV, Department of Physics, room temperature IV we can do low temperature IV also. So different 3 films were taken, and this is the geometry of the films, and we do the IV measure. These are the your rectifying type of IV, non-linear IV comes. So they exhibit distinctive hysteresis behavior, that is asymmetric feature which corresponds to the large resistive switching and rectifying effect. So these threshold energy, these are the threshold voltages where the current shoots up at that point. These are called the threshold voltages. They are 0.35, 0.95, and 1.5. They increase. For the increase in the film thickness, the threshold voltage also increase. So with the increase in the film thickness, these threshold voltage shift to a higher value, which is due to the decrement in the oxygen vacancies in the film thickness, which is again published. So these are the your non-linear IV curves. Non-linear IV curves for the after 2 volt of applied voltage. If you apply the 2 volts signal here in the 23 nanometer film, you get here. So resistive switching from high resistance to HRS to LRS is called a set process. So when you switch from the high resistance to low resistance, it's called a set process in a positive bias. Whereas exactly opposite, from low resistance to high resistance, is called as a reset process, and that is done under the negative bias. So it is a bipolar type of switching one can do here, and IV curves exhibit bipolar resistive switching behavior that we have observed in detail. This is a mechanism. This paper was accepted within 8 to 10 days because this is a very interesting mechanism which proved, which supported the observation of IV in this materials. So this what happens under the positive bias and what under the negative bias, how there is a majority charge carriers which are electrons, how they move, and oxygen vacancies how they move from one side to another side, which gives to LRS and HRS state. That is explained in this mechanism. I will not go into the details. One can read, you can read the publication also. So therefore these are some of the. Then retention behavior. Whenever you make any device or any type of a diode, and if you want to use it for the LRH, HRS application or switching, then it should retain its property for a long duration of time. So it has got a stable retention behavior. 23 and 63 nanometer films, they possess stable retention behavior. This 23 and 63 as compared to 43 nanometers film, because the switching ratio is 1.3 in 43 nanometers here. So with the increase in the film thickness, the defect state decreases, resulting in an observation of low on-off switching ratio for 43 nanometer film and 63 as compared to 23 nanometer film. So therefore the stable retention behavior and large on-off ratio in the BCMO film make a promising candidate for the application in non-volatile memory devices. So these are the we fitted from the, now this is academic point of view. After doing some what you call as applied, we have to do also some academics also. So therefore we fitted the IV data in the different type of the voltages. You can see bias voltages. So applied voltages less than 0.5 volts, it exhibits ohmic conduction. If it is in the range of 1.2 or above applied voltage, then we talk about the trap field limited, that is TFL type of the conduction takes place. And in the third region, the TFL curve to Child's law, because transition takes place from the TFL to the Child's law, which is very popular in our diode equation. We do the Child's law. So therefore the current increases rapidly with the slope of greater than 4, accompanying increase in the voltage of the films. So therefore there are 3 types of regions which can be fitted in the IV data now. So this is P loop, because this P loop, you can see that finally in 63 nanometer films, at least you can get some good P loop observed improvement in the electric behavior. Otherwise this is not a good P loop actually. At the low thickness film, 23 and 43 nanometer film, you don't get a good saturation of the polarization also, but you get some proper or some acceptable P loop when the thickness is larger now. And then finally I conclude here that these are the results which I could get and we could publish also. And I am not doing some applied work directly, but we are making the materials useful for applications. Basically I don't boast that we are doing some applied work or we are making device, because it is not our bread and butter, because we have got a very small laboratory. For making the device you need clean rooms, you need high quality substrates, you need large area film, but that is not possible. But we study basically the understanding, and then we develop the material which can be taken up by the applied people now basically. So these are some of the results which I could do here, and I could just show you one. And these are some of the publications in the last 7-8 years now. You can see from 2007, I think, from last 10 years and they are already there. And I have a lot of collaborations with national level. Basically, these are our students who have done work. First authors are always my students. So these are the publications which have come out from the recent research results, and these are recent publications. Okay, so these are some conferences, and these are there. And I'm thankful to my collaborators earlier, Dr. Ganeshan, who was the director of the UGCDA CSR Indore, and Dr. Fase, who was the acting director for 1.5 years, my friend from the Indore again. Ram Jane, who is active researcher, still there. Dr. Shukla, who is on the beamline working. Dr. Rajiv Rawat, Alok Banerjee, he was also acting director for some days. Dr. Reddy, Mukul Gupta for the high resolution XRD from Indore. Dr. Ashokan, who was my collaborator in IUC New Delhi. Dr. Sudhindra, who happens to be my student number 9 and who is a senior scientist in the UGCDA CSR Mumbai doing the infrared diffraction work for me. Dr. Dhanvir Rana, who is my student number 10, and he is a professor and head of the ICAR Bhopal Department of Physics. Dr. Om Prakash Thakur, my collaborator from the SSPL New Delhi. So these are some of my laboratories in the physics department. So these are there in the physics, which I have left almost 5-6 years before XRD. And then we have got a simple this thing AFM, very simple. Then DC sputtering, RS sputtering, which we use for our masters and this thing. This is my closed cycle for the 2 samples. I can do IV and RT, everything. And these are my facilities. And now in this new department now, this is my department. I have some facility. I have got STM now, room temperature STM. We have got a physical quantity measurement system for the IV up to liquid nitrogen temperature and the susceptibility also. This is my laser. This is my multi-target chamber. This is PLD, this is laser, excimer laser, and so on. These are some of the furnaces which are in working condition. And these are my plasma system which we develop for the master students. Now we give plasma as a regular practicals for the plasma, temperature of plasma, density of plasma. Then we do all these measurements of plasma. And this is a DC sputtering unit for the students of masters. They normally deposit the films and study their properties using the DC sputtering unit. Thank you very much. Thank you. Thank you.
Thank you, sir, for nice presentation.
Yeah.
Dear participants, if you have any query, you can interact with our resource person.
Yeah.
Participants, particularly our researchers, PG students, UG students.
Yeah.
If you have any query, they want to interact with our able resource person for this session, Professor DG Kuberkar, sir.
Yeah.
Actually, this presentation was very useful, particularly those who are working in the field of materials.
Yeah. Yeah, thank you.
I would like to share with you, sir, for this session, or for particularly for this conference, the people belonging from the other fields are also registered and they have participated here.
Yeah. Oh, good. Very good. Very nice. Very nice.
And from Madhya Pradesh, Chhattisgarh, and others. So
that's good. Very good. Very good. Very good.
Can interact with the.
Yeah. Anytime.
Please.
They can write to me
Anybody
also.
Want to interact with the resource person, he or she may raise her hand and ask the question, please.
Hello.
Yeah, hello, please.
Good afternoon, sir.
Good afternoon. Yeah.
Myself Sumit Patil from North Maharashtra University, Jalgaon.
Yeah, please.
Actually, I want to know about the PU loop that you have mentioned in your presentation.
Yeah.
So, how many parameters and which parameters we have to take?
Basically, the P loop, you can see, basically, you have to have a P loop tracer from the radiant technology. Basically, this is an imported unit, but this is very good P loop. You can do for the films also, for the bulk measurements also. Because you have to apply some voltage, electrical voltage also, high voltage, and then you can do the polarization. A lot of things can be taken out from that, because basically if you want to study the electrical behavior of the material, polarization, then because there are some Indian instruments also, but they are not that reliable because they are quite cheap also. But if you are going for the radiant P loop tracer, which is around 40-45 lakhs rupees, then you can have the room temperature P loop jigsaw also, one arrangement for your holding the film or the bulk sample, and then you can do the low temperature arrangement or high temperature. Mostly in P loop, low temperature is not that useful as the high temperature facility. So if you have a good furnace and all those things, you can do the high temperature, the polarization versus electrical field also. This P loop is very interesting. Yeah.
Yes, right. Thank you, sir. Thank you very much.
Thank you. Yeah.
Any question? Any participants would like to ask?
Yeah, they can write to me also, because my email, you can just put DG Kuberkar Rajkot. You will get all my details and my website, everything. And they can write to me also if they need some help for characterization, because I also go at many places, but now we are developing there also. So if somebody wants to make the films using PLD, if you are doesn't get the time in Indore or Delhi or somewhere in TIFR or BRC, you can write to me. I have some facility I can provide you. You have to only come with your target material. I can tell you what is the size of your target, and your substrate you have to bring yourself, and we can help you in making the good quality films also, which you can characterize subsequently at different places. Yeah.
Any question, please, from participants? Yes, if you are having any query, you may also contact personally to sir. Already display the mobile number.
Yeah, please.
If there is no question, then may I give the thanks. I'm
thankful
to Professor DG Kuberkar sir for nice presentation.
Thank you.
As his presentation will be nice and very fruitful for all researchers, particularly working in the field of material science.
Yeah. So thank you, organizers. Thank you, Dr. Sirsat. Thank you, sir.
Thank you, sir. So once again, I would like to thank the Kuberkar sir, morning session Professor Desai sir, and all the participants who have joined in the morning session. With this one, the morning session ends here. I would like to request all the participants to join in afternoon at 2 o'clock on the link which I have already shared on the group.
Yeah.
Thank you. Have a nice time.
Thank you.
In the afternoon session. Thank you. Have a nice time.
Thank you.